Okay. Stefania, can you hear me? Can we start? Okay. Sure. That's clear. Okay. So, good evening to everybody. I'm a bit nervous because I have here professors, friends, colleagues, students, so it's a very diverse and intimidating audience. Okay. To find the right level and to find the right way to talk about this stuff in a way that is interesting to almost everybody and not boring for people who are maybe already expert about this stuff. So the idea is that I'm going to talk about the innovation in biomedical imaging, X-ray imaging, and I want to start just a little bit with some history. I really love the history of this stuff, but I cannot spend too much time on it because I realized that if I started with too much history, then I didn't have the time to discuss all the application. But there are a few things that I think are very interesting, at least to mention. Okay, so the story starts with William Röntgen, the professor that you see here during his holiday time in the Alps, and his wife, Bertha. You know, you hear why also his wife is important in this history. So the thing is that Professor Röntgen was a professor in this university in Germany, and at the end of the 19th century, he bought some of these fashionable vacuum tubes that were used at that time to study discharges in the vacuum tubes and the production of these cathode rays in these fluorescent bulbs and tubes. And he started to immerse himself in the study of these cathodic rays and these discharges in the October of 1895. So just, let's say 1 month later, in an evening of the 8th of November of the same year, he was studying these discharges in a darkened room and with the X-ray tube, which in that moment was covered with black paper, and he realized that he was seeing some fluorescence on a screen that was in a table far away from the experiment he was doing. Cathode rays could not travel through air. This was already demonstrated by Lenard, and so he didn't understand what was the matter and what was the cause of this scintillation of the fluorescent screen. So he started to check for the correlation of these cathode rays and the scintillation, and he realized that he was dealing with some kind of radiation that was yet unexplained and not known. So in the next few weeks, he started to experiment a lot in trying to understand the properties of this radiation and to understand the properties of attenuation of different materials until slightly before Christmas, you see it, the 22nd of December of the same year, he asked Bertha, his wife, to give him a hand in research, literal hand, and he made the first radiography, which is quite famous, the radiography of the hand of the wife, which he entitled Photography of Hand and Hand. So in the next few days, he prepared this communication that you can see here, which was entitled On a New Kind of Rays. And this communication you can see here that was submitted to the Physical Medical Society Journal, the local Physical Medical Society of Oslo. So you can understand that it was already in his mind that this was an important discovery, not just for the science, but also for the possible application in medicine. And it's not written here, but the truth is that this was the first journal that was publishing at the moment. Okay, he was suspecting that somebody else could discover these X-rays, so he also exploited the first available physical communication in his town, which was this one. And so probably the two things are a little bit interlaced and interconnected. And the news traveled fast. Just a few days after this first communication that was printed on the 1st of January. It was a front-page news in Vienna the 5th of January, and it was already in the US, published on the New York Electrical Engineering Journal, 8th of January. Then it was on Nature and on Science, and let's say the news was global, just after less than a month of the discovery. An important thing, I think an interesting thing, is that also the translation to clinic was immediate. You see that within almost 2 years, let's say, the physician and the physicists were already experimenting this kind of radiation application in medicine to find foreign objects or detect fractures and this kind of stuff. And in the 1987, there was already at the new, you see, Royal Infirmary in Glasgow, it was open an electrical pavilion, so the electricity delivered to the hospital, and they installed what we can call the first radiography department in the world. And this was just 1 year after the discovery. Okay? So in terms of what we call now maybe technological transfer, you can see that apart from the major breakthrough, the discovery of X-rays, of a new kind of radiation in a period in which modern physics was still completely unknown. So this was one of the first, let's say, seminal experiments and discovery for modern physics. The spread was fast and global and immediate due to the fact that this technology was available, because a lot of people were studying with these vacuum tubes and discharge, let's say, in this kind of tubes. And so it was accessible and reproducible. Okay, so we have an immediate technology transfer. And obviously, also in the, let's say, general public, it was quite a new, exciting discoveries, and you can see that many, let's say, funny or strange applications were found for this kind of radiation. So this is a very nice photo. Röntgen became immediately a worldwide celebrity. They had a statue of him in Berlin, and he won in 1901 the first Nobel Prize in Physics for his remarkable discovery of the X-rays that were subsequently named after him. Not worldwide, because just in Germany called still Röntgen rays, and in the world we now called X-rays or raggi in Italian, which is the name that he gave to the rays at the beginning. So apart from the history, and we see why some of that will be useful in the next slide and interesting, I want to talk a bit about the basis of radiography. Okay, for somebody, I think that these things are at least intuitively very common and understood, but I want just to put the basis for the discussion. So everybody knows what radiography is. What we have is a source of X-rays, and then we get an image, which is something that represents a map of the X-rays attenuation across the sample. Okay. From this information, or from this attenuation, what we can do is we can obtain morphological information based on the photon attenuation. Okay. What I typically use when I do events with the general public is the analysis with this image. But obviously, with you, we can go a little bit more in detail, because we know that when we talk about X-ray attenuation, we can describe it with the general Lambert law that tells us that a certain thickness X of a material will attenuate a number of incident photon and zero as the negative exponential of the product of the linear attenuation coefficient mu and the thickness of my sample. Okay, so what I have, there's something wrong with the image. Anyway, what I obtain when I do what is now common, that is a digital radiograph, is that for each picture element, or for each piece, and you definitely know what they are, I can associate a certain value, which represents a gray level, which is somehow related to this mu times x. Okay, so the attenuation of the photons. So if we now think of the same thickness, in order to have a different signal, what I need to have, a different attenuation coefficient. Okay, and here I represent the attenuation coefficient on some of the material which are interested in medical or biological fields. Okay, so you can see some kind of tissue, adipose, brain and muscle and water, which are the so-called soft tissue that you see here in the lower region of this graph, which represent the linear attenuation coefficient as a function of the energy in kilo-electron volt. So what we can see is that here we define a certain energy. The difference between this in orange, which is the bone tissue, and the so-called soft tissues below, is quite great. Okay, there is a huge difference. And in fact, in radiography, you definitely can distinguish between the bone and the rest of the soft tissue. Instead, you can see that if we zoom in this region, all the soft tissue basically are, as we can say, very close, okay, to each other and very close to water. Okay, so obviously it's very different with a simple radiography to distinguish between different soft tissue. Okay, what we can do is that we can try to affect selectively some of those tissue, if you want, by adding a so-called contrast medium or some material, as in the case of iodine, which is the one in blue that you can see here, which has a definitely higher absorption coefficient than the soft tissue. And if we can selectively addition it to the features that we want to see, what we obtain is an increase in contrast. And this is the idea at the base of the so-called contrast medium radiograph that were immediately, let's say, experimented, not in vivo at the time because these contrast medium were a little bit, let's say, harmful, okay, but in order to obtain anatomical images in which we could understand, for example, the so-called angiography or the blood vessel inside these samples. Okay, so X-rays since the beginning, apart from the diagnostic, were an important tool also in order to get a better grasp of the anatomy of the body with these techniques. So to sum up, when we have radiography, what we have is basically a 2D projection. Okay, so we have an information which, if you want, is monoparametric, that with respect of the position give us an information regarding this product of the attenuation coefficient and the thickness of our sample. It's not possible so to disentangle the information between thickness and absorption coefficient. What you obtain is something that is combined. So something that is very absorbing and thin can give you a signal as something that is very thick but with an attenuation coefficient. Okay, let alone if we have a combination of different material with different thickness. How can we try to disentangle this? You probably already know that we have at our disposal the so-called X-ray computed axial tomography, or just tomography, or CT in English, in which instead of getting a radiography which would be a projection of a volume on a 2D surface, what we can obtain is the radiography of a slice of that object. I bet that you are familiar with this, and you have seen this kind of devices and how it works. Basically, the idea is that we can, by making different radiographs around our patient or our sample for this thin slice, so we make radiograph with different orientation, we can reconstruct the 3D information, and we can reconstruct the slice, and by making many of those, we can have a volume reconstruction of our patient, which we can reslice in different view in order to obtain and to disentangle the information between the propagation direction and the across the propagation direction between the linear attenuation coefficient and the thickness of our sample. So the content of each now called volume element, no more picture element, so something that is related to a smaller volume that we call voxel, will be related to the attenuation coefficient mu of the material within that voxel. Okay? So you could say, very well, so if I know the attenuation coefficient, I can, by knowing the energy that I use to make the radiography, understand what kind of element or material that was. The thing is that we can remember that this attenuation coefficient is in truth the product, if you want, of the mass attenuation coefficient, which is something that is related to the composition, actual composition of the material. So the atomic number and the atomic mass of the material and the energy of the photon that we are using, times the density of the material. Okay, this might seem trivial, but the point is that this number, so the mass attenuation coefficient, depends only on the actual composition of our material, so on the chemical properties, if you want, of it, while rho is something that can be depend on the physical state, and in particular in biological samples can vary depending on the state of the tissue or the material that we are considering. Okay. In fact, what can happen is that if we make a radiograph, for example, at a certain energy, let's consider this one, 100 keV, and our hidden volume is a volume composed just of bone, which would have this attenuation coefficient, or iodine with a concentration that is, let's say, not a complete volume iodine, but a solution of iodine with a certain concentration that gives us the same attenuation of the energy of the bone. So we cannot understand if the voxel that we have imagined is a voxel of bone or a voxel of iodine. Okay. Nonetheless, CT revolutionized the clinical diagnostic routine, and in 1969, Hounsfield and Cormack received the first Nobel Prize in medicine for their development of the computer-assisted tomography. So definitely it was a major breakthrough. And so up until now, we had two major breakthroughs in diagnostic X-ray imaging. Sorry. The first one was the introduction of CT. Okay, so from projection and bidimensional radiography to CT, and the second one was the advent of the so-called digital radiography, because it might seem counterintuitive, but we got CT before the actual spread of the digital radiography. Okay. Despite these two breakthroughs, in order to get radiography, we still rely on the same working principle to generate radiation, and we'll see something about that later. But the thing that I want to stress is that the image is still a map of the integral X-ray beam transmission of our sample. And the point is that the detection of the features of interest for a particular diagnosis are still critical in the case we have low contrast details in complex anatomical structure. Okay, you can see an example here. This is a detail of a mammography in which now obviously none of us is a radiologist, but the point is that you can see that in this image, I'm telling you, okay, obviously it's not visible, but there is a lesion, okay, that in this condition is not visible due to the fact that you see that we have a lot of surrounding material in a complex anatomical structure that masks the detail that we want to see. So what are the goals of the research and what we want to move on from this? The idea is that we need to increase the diagnostic power, and somehow we need to, if you want, act on the signal-to-noise ratio of the structure. So in order to act on the signal-to-noise ratio, what we can do is either increase the signal or try to reduce the noise. And the approach is that all the effort goes in trying, from this point of view, to increment the contrast of, sorry, here there is a typo, so increment the contrast between, maybe a bit like this, of similar absorbing tissue, meaning of what we want to see with respect to something similar that we don't want to see, okay? Or to try to isolate the signal of the filter of interest from the background. That could be noise coming from the acquisition or the so-called anatomical background, so the structure surrounding and masking our signal. And we want to do all of this by minimizing, at the same time, the radiation dose, the risk, or the discomfort for the patient. So, where can we get more information with respect to just the simple attenuation of the X-rays that we have discussed until now? And the idea, here I put this picture because it's cool, okay? But the idea is that here you can see all the two processes that processes or let's say ideas that I want to discuss. One is the spectrum, okay, so the different energies that we can find in the radiation, and the other is the process of diffraction, or if you want, the change of phase of the radiation while it has a process of humidity. So if we start with spectral imaging obviously is not this kind of spectrum, but it's spectral in the sense that it's a class of imaging method that want to exploit the information which is derived from X-ray measurement at different energies. Okay, something related to the energy spectrum. In order to do what? To better differentiate or to classify tissues which are similar from the point of view of absorption, or to obtain some information that might be quantitative and absolute that can help in characterizing the tissue in diagnosis. Okay, so basically, in order to try to disentangle this problem of the measurement of the mass attenuation coefficient as a product of these two things that we just discussed. So how many energy do we need in order to do this? Well, let's start with two energies and we'll see why this might be more than enough. And this was a seminal paper in 1966 by this Alvarez and Makoski, which proposed a method in order to make this kind of energy selective reconstruction. What is the basilar idea? Well, it is quite simple. The idea is that the attenuation coefficient of any material, okay, is the sum of the attenuation due to the photoelectric effect and the Compton effect. And you say it's not true. These are not just the two components of the complete attenuation. But the point is that it is true while we are in an energy range, which is the one typical of diagnostic imaging, which is between, let's say, 10 keV and 150 keV. About, okay? In this energy range, the two main components of the linear attenuation coefficient are the photoelectric effect, which has a steep power dependence on the energy. Okay? It depends on the energy to the -3. And the component effect, which has a slightly more complicated dependence on the energy, which is described by the Klein. Okay, so the idea is that we can write any attenuation coefficient as a linear combination with two coefficients A1 and A2 of this photoelectric energy dependence and the Compton energy dependence. These two parameters A1 and A2 are related, you see, to the density of the sample, but in the case of the photoelectric also to the atomic number to the fourth power, and in the case of the Compton, with this relation that you see here. Okay, so if you consider that Z of A is pretty much constant, this is just related to the density. So what is the idea? Is that if we can acquire two radiographies with X-rays at two different energies, okay, what we can write is two equations in which for each of our voxels, what we are evaluating is the attenuation coefficient at one energy as this combination, and the attenuation coefficient at the other energy as this combination. So we have two equations, two unknown, and we can solve it in order to obtain the coefficient A1 and A2. These coefficients are related. We'll obtain one of these for each voxel, and these are related to the composition. So basically the atomic number of our material in that voxel and the density of the material in that voxel. Okay. So this was from the original publication. You see, they proposed that each different tissue had a different couple of these two numbers determined by the composition and density, and so it would have been possible to disentangle, let's say, distinguish and differentiate these different materials. Okay. Probably you have never seen this, but you definitely have seen this in some airports. Okay, this is the same technique which is used in the airport security in order to make a color scale in which each pixel of our radiography is differentiated, and it's in this case blue when it's something high Z, typically a metal, organic in orange, and something in the middle, which is the green one. Okay. this kind of approach, as it might be seen interesting and understandable from a physicist point of view, is not so useful or readable by somebody which works in the clinics. Okay, in the clinics, what is more important and often more used and more interesting is to make the so-called two material basis decomposition. So the idea is that, just reshuffling what we have seen before, we can write the attenuation coefficient of any material at a certain energy as a proper linear combination of two absorption coefficients of two different materials that we chose as basis. Okay. If we do so, and we acquire again two images at two different energies, what we can obtain is, for the two bases that we have chosen, for example, it could be either bonds or tissue in order to better differentiate water or iodine, one or iodine, different combination, we obtain N2, N1 and N2, sorry, which are the fraction in that voxel of the first material and the second material. Okay? If we assume, and often this is true, that in that voxel we have a composition just of two materials that we are considering, I think that the battery is that. If I speak up, can you hear me, or do you prefer to?
I can hear you. Does it work? No,
Sì, sì. So this is the two material basis decomposition, and the same approach. I forgot to say we were talking about computed tomography, but the same approach works the same for planar radiography, with just the substitution that what we are obtaining is not just the density, but is the density times the thickness. Okay. Is this in use? Is this working? And the answer is yes. You can see, for example, here some figures taken from this review in radiology, in which it's possible to see here the differentiation between iodine and bone in the case of angiography, the differentiation between iodine and calcified plaque stenosis in order to assess the stenosis of this blood vessel, or to differentiate a different type of calcification that can distinguish between the diagnosis of arthrosis and gout in the case of rheumatic disease. So, what is the research if we already have seen the images?
Io ho fatto lezione prima.
Occhiali non distinguisce.
Ok, sorry.
So, is there already an implementation of these techniques? And how can we implement these techniques? Well, there is a way, which is either by determining the energy using the source. Okay, so we have a detector which is not sensitive to different, not sensitive, not able to distinguish between different energy, and we change the energy by acting on the source, or we use a multi-energy beam, a polychromatic X-ray spectrum, and we make the energy determination and selection using spectroscopic capabilities of the detectors. Well, what you have seen and what is in most of application done at the moment is on the first category, so using the source in order to determine the energy. Okay, and this has some limitation. Okay, despite the nice result that you have seen, there are several limitations with the broad spectra that we have available in the energy emission and the energy overlap between the two energies that we want to use. Okay. So let's say that the research in this field from this research group, from the research group of medical physics in Ferrara, is quite, let's say, long. And here I just reported a few, not a selection, but just some copy-paste of some of the results of the group in which I was not there, because if you can see, we go from 2002 basically to a few years ago, because this has been always an active research in Ferrari, in particular in the case of mammography, and in particular dealing with the sources and the development of sources in order to do that. Okay, I was not there for most of the time because here I was still trying to understand if I want to study physics. Okay, and so what I want to discuss now is something which is more related to the researches that we are doing in this field and what we are going to do in the next few years. If there is any students here interested in possible thesis work and understanding what it can be some research activities with our group, so we will be probably related to this. And so it is something which is related to the part I was saying of the detector. So when we want to discriminate the energy that come out from our patient by using the detector and not the source. So typically all the detectors that are used in the common practice now, in clinical practice in radiography, are the so-called energy integrating detector. And the idea is that they work the same as the old film, radiographic film. So we get, for the time of exposure, we open our detector and we integrate all the energy which is deposited on a certain active volume, and we take the signal and make the pixel gray level for that pixel. Okay, so we integrate for the entire time of acquisition. We integrate the signal. Instead, if we want to obtain an information instead on the energy distribution of the photons, what we need to do is we need to measure the energy of each of the photons incoming in order to keep the information of the energy together with the intensity that we record. And so the idea is that we have a class of typically solid-state detector in which for each photon, what we do is not just counting, but also integrating an information which is proportional or at least related to the energy of the photon. Okay? Why this is not done routinely? Well, because the rate, in particular in CT application, but also in common radiography, the rate of photon coming can be up to 10 to the 9 counts per second per square millimeter. And this kind of rate is very challenging from the technological point of view in order to be able to track this kind of information. There is a couple of activities that I want to describe now that are somehow putting together these two stuff. So the detectors and the spectral approach and dual energy approach. And the first one is this active collaboration that we have with the Rizzoli Orthopedic Institute, which is in Bologna, here close to Ferrara. And with them, we are studying this class of innovative contrast media, which are still based on iodine. So the contrast medium is iodine, but instead of the typical angiography, where we inject iodine in the blood circulation, these have specificity to be diffusing in cartilage tissue. So if we have this kind of sample, which is a little sample taken from a bovine tibia, I think, and there is a little bit of bone, and here we have the cartilage. If we make a radiograph or a tomography of this object, what you see here is the structure of the bone and nothing here, which is the cartilage, because the cartilage absorbs basically like the water, which is, let's say, the medium in which this object is immersed while we make the radiograph. Okay. Instead, if we immerse these in a solution of this contrast medium, what we have is that we have a selective captation of the contrast medium in the cartilage, and we are able to actually see in the radiograph the cartilage. And more of that, if we can make spectral imaging, and so an imaging at 2 energy, the idea is that we can try to distinguish between the cartilage and, the iodine that is in the cartilage and the calcification of the bone in order to well differentiate it to tissue and make a better diagnosis of the status of health of this interface between the cartilage and the bone. Okay. So here you see the first measurement that we have made in collaboration with this Pepi Lab, which is in Trieste, is a friend of ours which is working in Trieste, who put together this system in which there is a common X-ray tube. Here you see our sample, and they have available this detector, which is called Pixirad, which has the property to be able to acquire, make acquisition with a set of a threshold, and the threshold is here was set it at 33 kV, which is the K-edge absorption of the iodine, and to give us the count on each pixel on above the threshold, okay, which would be this part of the spectrum, this was the total incident spectrum, or below the threshold, which would be this part. So what we can obtain is by a unique acquisition, obtain simultaneously the images at two energy levels, the high energy and the low energy. By applying the method that I described previously, these are very recent results because its acquisition is just a few weeks old, okay, so still unpublished. So by making the dual energy decomposition on different bases, for example, iodine, sorry, and water, we can, you see, separate and distinguish the two materials, or in a different basis, iodine and hydroxyapatite, which is the mineral part of the bone, distinguish between very well between the interface of where the cartilage ends and start the mineral part of the bone, which are fundamental in the diagnosis of osteoarthritic disease and on some mechanical structure of the cartilage to assess its state of health. Apart from that, in which we are, let's say, working more on the reconstruction and on the contrast video, from the side instead of the detectors, there is this project, which is the project MEDPIX4. And the thing is that INFN, thanks to the effort and to the, let's say the effort of Professor Fiorini, which is here with us, Seminario Fiorini, in 2020, INFN became a member of this international collaboration, which is based at CERN. And this collaboration is aimed at developing two particular readout chips in order to produce some hybrid detector. And the collaboration is making two of these two types of these chips. The MEDPIX4, which is which aims to the realization of spectroscopic X-ray imaging detector, in particular compatible with CT scans, okay? Or the MEDPIX4, which is instead more oriented to particle identification and high timing precision. Both of these, the important thing is that they are going to be fully prepared for this through silicon via processing in order to have them without that region on all the four sides. So even if these are not particularly large, they will be possible to be let's say, butted and placed one sided with the other, and to obtain large areas detectors. Okay, so there is a project with the same name, which is funded by an INFN Field Commission or by the FEN for Technological Research, which is currently ongoing and is studying the application of this technology in a wide range of fields, from spectral imaging to nuclear medicine and dosimetry. And in particular, here in Ferrara, what we are doing as a medical research group is that we are collaborating with the part which is more of detector development of Professor Fiorini, in order to characterize the X-ray imaging performance of this device and to study the possible medical spectral, let's say, imaging application in the biomedical field, in particular for mammography and osteoarticular imaging. Okay. This is a very recent activity. We are starting, I think, very soon to make the first characterization with radiation and measurement, so it will be something that maybe we'll have some results to present, I hope, in the very close future. Apart from the energy, I was saying the other possible way to get more information than just absorption, we see what we can do by discerning the energy of the photon, is something which is related to the phase of the photons. And historically, they say that since the discovery, Röntgen tried to understand if there was refraction by the X-rays, but he couldn't find it. Okay. And instead, just almost 30 years ago, the Nobel lecture of Arthur Compton, when he was given the Nobel medal, he made the classic, let's say, Nobel lecture, was entitled X-rays as a branch of optics. And he made this statement that even at the time, it was hardly, at the present, is hardly a phenomenon in the realm of light whose parallel is not found in the realm of X-rays. Okay, so there is a perfect analogy, obviously, between the interaction, if we want, of matter, of light with the X-rays. So even if it's, oh no, sorry, this figure appears a bit strange, nonetheless, maybe it's understandable. So the idea is that whenever we have, we can imagine, sorry, a parallel wave incident on a certain sample. Okay. What we have is that we have an effect of absorption, but also we have an effect of refraction. But these X-rays, which translate, or if you want, of a change of phase of the X-rays, which translate into a deformation of the wave plane and to a phase shift of our wave. What we can do is we can describe, as you might have already seen, the refraction index in this way with a complex real part which is related to the amount of the phase shift and a complex part instead which is related to the absorption part. And the phase shift will be given by the multiplication of the wave number times the integral of this phase shift part of the refractive index along our sample in the direction of the propagation of the X-rays. So why is this interesting, sorry, for imaging? Well, the point is that this part, so the part related to the phase shift, is for low atomic number materials, is 3 orders of magnitude larger than the part related instead to the absorption phenomenon. Okay, so it's a phenomenon which is very intense for low atomic number. But more interestingly, what happens is that what you see here is as a function of the energy, the difference in the real part, so the phase shift, which is this one between the tissue of muscle and adipose tissue, so very similar tissue, compared with the difference instead of the complex part, which is the one related to absorption. This means that the difference in phase shift by similar material, such as muscle and adipose, is way larger, orders of magnitude larger than the difference instead in absorption. So something that we cannot appreciate in absorption, we might appreciate in differences of phase shift. So how can we use these for imaging? Because the point is that for wavelengths which are equal or larger than optical photons, we cannot possibly measure directly the phase of the electromagnetic wave. Okay, so the only way that we have, as in many other physics fields in which we deal with the phase phenomenon, is to use something that is an interferometric, if you want, approach, or something that translates this phase shift into an intensity change, because the only thing that we can detect basically is the intensity of photons, okay, of electromagnetic waves. So there are many possible approaches that are studied and experimented, and many of these are also quite complicated and clever. And obviously, I don't have neither the experience or the time to describe all of them. I just want you to describe a couple of these in order for you to get the idea and to describe a couple of research activities. And the first one, which is maybe the simplest one, is the so-called free space propagation. So the idea in free space propagation is just quite simple, if you want, in principle. and is to just distance the detector from the sample. So you have a sample here and let's say a plane wave incident on your object or your sample. And what you do, you take the detector and you move it away. What you can see is that if you go at the right distance, you will see arise the effect basically of interference between the refracted and the original plane wave. You can see this effect represented in this figure. This is the radiography of two human hair. Okay, so it's just human hair crossing, imaged or radiographed at 20 kiloelectron volt at a synchrotron radiation, and you see that when we are in contact or very close with the detector, we don't see any contrast here. As we move away from the detector and we from 20 to much is that 1 meter and something, we see arising these fringes of interference. You see a profile here, and this is called the so-called edge enhancement effect. Okay, so there is no gain in this case in the absorption of these two objects, but we can see the border of the object, and we can see so an enhancement of the edges of very low absorption samples. How can we use these in radiography? There were studies in order to understand if this would have been a useful effect in the case of mammography, in which one of the challenges is to understand the borders of lesion and let's say structures which are suspect to be malignant lesions, and so having a edge enhancement effect should be helpful in order, you see, to now I don't know if with the quality of the projector or something is actually readable, but the point is that this is the same image taken with a conventional mammography system, and this is the one taken with the synchrotron, and the point is that the radiographer were able to better detect the actual border of the lesion and to make a better diagnosis. Okay, there was this clinical trial that went on at the Electron facility, which is the Italian synchrotron, 2 years ago. The conclusion is that the images are good. There is an advantage also in dose reduction thanks to the monochromatic properties of synchrotron radiation. What is the only problem is that obviously we cannot translate these to clinical routine because synchrotron radiation are not, let's say, sustainable from the financial point of view, and so they cannot be translated into clinical routine. Okay. The requirement for this technique is to have a very small focal spot and a very intense beam, so there is no an actual possibility to transfer this kind of approach to clinical practice in a compact and cheap way. There are other techniques, I just want to discuss one more, and you will see why just very soon, which is called edge illumination. And the idea of this technique instead is slightly different. In this case, we can use, let's say, a common X-ray tube. And the idea is to put a mask. You can imagine something which is radio opaque, so stopping photon with a lot of holes in regular position, okay, which creates this beamlet of radiation. And this beamlet of radiation propagate, and before our detector there is a matching mask. You see it here, and you can think that in the case of no sample here, you will have your beamlet getting to the pixel element, sorry, to the pixel of the detector without absorption but our second mask. Okay, whenever we put inside a sample, what we have is a refraction of this beamlet, and so changes in the direction. And what happens is that they will intercept part of the mask, and so we will have a reduced intensity. So the idea is that by scanning this detector mask in front of our detector, we can use this as a sort of analyzer in order to sample how the signal that, sorry, with changes with respect to the mass displacement. Okay, so without the object, the signal was the one represented in blue. When we have the object, for each beamlet, we have a different, as I said, direction, and by scanning our mask, we will obtain a different profile. Okay. So what we can do with this scanning procedure is that by analyzing the changes of these two profiles, what we have on for each beamlet without the sample and with the sample, the shift of the two peaks gives us the refraction and so the phase information. The difference in the height of the peak gives us instead the transmission, okay, because it's just the absorption, while the spread of these two is an information which is about the ultra small scattering angle, which is related to something that we won't discuss, but is structure which are smaller than the scale of our pixel. The point is that with this solution, it is possible to have more relaxed requirements on the X-ray source, so it is possible to realize this kind of system with common sources, okay, X-ray tubes and not single radiation, and so to have a more compact and affordable implementation. And this is, for example, the radiography of a bee. You can see maybe the head of the bee and so on. So this was the transmission, this was the refraction, and the scattering in a sort of composite. The same was made of very high energy. This is the photo camera of the smartphone. And you can see that in the refraction, you can see the difference in the lens of the photo camera, which were visible instead in the attribution. So,
What is on the left? Sorry. What is on the left?
On the left is a bee.
Ah, okay.
A bee, a common bee, an insect. Okay, so this will be the head, this will be the legs, and so the idea is that you see that you have seen this logo already. It's the Pepi Laboratory in Trieste, and the idea is to combine spectral and phase effect in order to characterize osteochondral or cartilage and bone sample from the ristoli, and we recently 1 year ago now submitted a print for this kind of research. So we are waiting for the result, but still we are working on this kind of applications. Last but not least, a very new project which has started this year, which is called the SPEREX project, and the idea here is to combine this time at synchrotron Electra, so with the colleagues in Trieste, in Pisa, in Rome, and here in Ferrara, to combine the spectral performance and the phase sensitivity of the synchrotron for small animal, basically diagnostic, and I will go into the detail. What I want to acknowledge here is that this is a collaboration with the Crystal Technology Lab, because in order to do this, we need some very highly specific crystal for X-ray manipulation, and so the local responsible for this activity is Laura Bandiera for this part. I will go quickly because the time is almost up, and this is just the last thing, and I don't want to spend too much time on this, sorry. And it's something instead about the source, which puts together what we are seeing now. So the X-ray tube that is used nowadays in all the radiographic application is basically works on the same principle of the X-ray tube that was the vacuum tube that were used in order to make the discovery of X-rays. Okay, so we have a cathode, an evacuated tube, the electrons are emitted and accelerated by an electrostatic field, and we obtain radiation by brainstorm production. Okay, so significant progress has been made in the engineering and the high voltage supplier and so on, but basically the operating principle is still more than 100 years old. And it has some limitation. One is that it has this wide, broad polychromatic Bremsstrahlung spectrum, And the other is that is very limited, it's limited, let's say, in radiation yield, and we always have a trade-off between the X-ray output and the focus spot size. So let's say that if we make an analogy with what we have done with visible light, in this year we have passed from the old incandescent bulb to neon light to finally LED light, and we have available also monochromatic and coherent sources, portable, which are the laser. Instead, with the X-ray tube, we are still in the region of the incandescent bulbs, and so there is a need for a change of paradigm and for a new way to produce radiation with better characteristics in a compact and affordable way, which can be used in the lab and in the clinic. One of these ideas might be, even if it's not ready at the moment, inverse Compton scattering. And I will spend just a few words on this, because this would require another seminar. And the idea is that inverse Compton is a process in which we have, instead of the classical, let's say, Compton scattering, a relativistic electron and not an electron at rest, which transfers part of its energy to a photon, and the photon is scattered back with a higher energy. So it's a way to basically, with an accelerated electron beam and a laser beam, to obtain in the backscatter direction X-rays. Okay. Now I want to discuss the detail. We have the discussion. I'm always available to discuss this kind of stuff. But what I just want to say is that this is a good candidate, let's say, for the production of brilliant, monochromatic, and tubable X-rays. And this will be at a fraction of the cost and the footprint of a synchrotron source, because the energy for the acceleration of the electron are 1 or 2 orders of magnitude less than what is required for synchrotron. There are several proposal or project in commissioning, or just one operational source of this kind in Europe, and we have been working on this stuff. In particular, I've been working on this stuff for several years now, and so we are involved in several proposals for the realization of inverse Compton sources in Italy. We'll see how these things go, if we can find the fundings for resources, and we are collaborating with the only operating inverse Compton source, which is in Munich, which is MUCLS, and still working on this stuff. Now I will close, and maybe we can discuss this thing with the questions. So just a couple of final remarks in order to close the presentation. So after the review of the basics, let's say, of conventional radiography, we have discussed spectral imaging, and let's say for spectral imaging, in particular for dual energy, there is already an implementation which is partially available. We have also the first photon counting CT, which came out last year. Yet many improvements are still possible in terms of contrast media, sources, detectors, and methods. So there's a lot of research going on. The phase contrast, instead, the clinical translation, let's say, phase contrast is around, it's been around for 20, 30 years too. And the point is that the clinical translation of this technology seems to be much more difficult and complicated. And there are several limitations for the characteristic of the source, the devices required for the many techniques, and the resolution of the detector. Nonetheless, even if the actual clinical implementation might be far away, these techniques are very interesting in the case of biomedical samples, when the objects are small, the field is reduced, and we don't have the problem of, let's say, time and duration of the examination. So these are still and will be very interesting techniques to explore in the future. On the part related to the X-ray source, instead, a change of paradigm is yet to come. Okay, so we are still working with something which is more than 100 years old, which works very well, don't get me wrong, but I think that in the future we will have somehow a change of paradigm within these respects. I didn't mention artificial intelligence, because that is a whole another beast, and so just a provocative, let's say, question: if artificial intelligence in medicines will be just an assistant or something to check and help the processes and the clinician, or will actually be a revolution for the diagnostics. And thank you for the attention.
Questions? Time for questions. Super.